Let's take a look at sound generation on the R32V2020. How about making a grand piano, having the frequencies of grand piano? That sounds like a good first target here. Wikipedia has a nice page on grand piano frequencies that in the white section here shows the keys frequencies for the grand piano from the high to the low. The middle of it, of course, is middle C at 220. And towards the bottom the frequencies go as low as 27.5 hertz. So making something that goes over that full frequency range would probably be a good goal. So let's take a look at doing that and start into it. Starting from the Wikipedia table, if we take those notes and the frequencies that respond or are used and translate that into how many bits we'd have to have a counter that goes up to 909,000. So 2 to the 20th is 104,000. If we take most significant bit and make it a divide by 2, then that gives us 19 bits of counter and 1 bit to divide by 2 to make sure we get a symmetric output. And if we fill in all the numbers here and figure out what we got to do, it gives us all of the scale factors that we'd have to have. And that's what the table looks like. Middle C here is right in the middle with a number of E8, A, B, C for the scale factor. To hook up this physically, I have a little audio amp with an LM386 on it and a little speaker that we're using to hear the sound out. We're going to start out with just the square wave, and this is all unshielded, so I have a little bit of hum on it, but it's really not too bad. Later add a scale factor, resistor, and capacitor to do some wave shaping and some scaling down, because the 5 volt or 3.3 volt swing of the output pin on the FPGA is just way too much for an audio amplifier. Here's a closer look at the audio amp. It's got a pot for adjusting volume, and we're just hooking it up with alligator clips, so again it'll be a little bit noisy hum wise, but should be fine for the test that we're doing here. Here's the assembly code for the function of making sound. Basically we're going to have 8-bit notes, where later we'll add an enable bit, but at this point it'll just be 8-bit notes, and they'll count up to the terminal count. So there's 87 notes or 88 notes, and we'll have a little delay time here so that it'll be on for a quarter of a second. Play with that number and then write that number to the 7-segment display. And down in here in the notes we just write that to the control register, and we'll take a look at the VHDL code for that and sit and increment the notes up all the way through the scale and see what we get. For the VHDL code, we'll have a single 8-bit register that we write to from the CPU. That top bit of that register will be an enable bit to turn the sound off and on, and it'll come up off with that bit 0. To turn the sound on, we'll write out a 1 in the most significant bit of that byte, and then down inside of the code here we'll play with the actual frequency. We created a wavetable table file that gets loaded as in lookup table values instead of RAM. I don't want to pick up any RAM, and the table will take that 7-bit note and turn it into the preload for the counter, and we'll have that 19-bit counter that we talked about earlier, I mentioned earlier, and that gets loaded from, basically those 8 bits get loaded from the CPU, and a single bit out for the sound value. So it'll just be a square wave to start with, and we'll do some wave shaping on it later on to clean it up. Basically the code's fairly simple to do that as just a loaded counter, and here's that code. This is the code with the enable bit added that turns off and on the sound. Basically, if you turn on the processor, that bit is low in the register, it's reset, and when you enable that bit or write a 1 to it, it'll turn the sound on. So any note we produce, we're going to have to make sure the most significant bit of that control byte is set to a 1, and that'll make the tone come on. And here's a capture of one particular note, and you can see it's 1.76 kilohertz, which matches the frequency we were going for. It's a very nasty square wave though when you listen to it, and we'll play a little clip of it just to see how bad it is. For debug purposes, I'm writing to the display here with the note, and this is before I set the enable bit on with the earlier test of it, and it's doing the notes. They're going up 25, 26 hex all the way up. And here's that frequency sweep as the note gets incremented up one by one. It's not set to scale on the screen for a little bit here, but you might be able to see the frequency change for the notes here as it goes along, going up through the entire set of scales. If we add a little RC circuit, it's a 4700 ohm series resistor there at R1, and R2, 100 ohm, makes a nice little voltage divider to scale that down. And then adding a capacitor C1 across the R2 will round off those nasty falling and rising edges. Doesn't make a good sine wave out of it, and it's has a cutoff point, so scaling that, I think I ended up with a 1 microfarad when I was done, and I think that was a better choice, or no, 0.1 microfarad, better than the 4.7, because it didn't attenuate as much at high frequency, but it worked perfectly fine. And the assembly code is just as simple as putting a sequence of longs, a table of those in with notes that correspond to the spreadsheet. And then calling set note, doing a delay for how long you want to make the note, and then a delay between notes. And those obviously could be adjusted in full and quarter and half notes, and all of those things could be scaled in as well. But this is just a very quick, short demo program. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.